for. Okay, so hello everybody. Our third speaker is going to be Matías Villagra, who won the MIPLIB competition this year and also the most popular award. Well, Matías is a PhD student in operations research in Columbia University, co-advised by Dan Bienstock and Yuri Fansa. He works on large-scale and computationally challenging mixed integer nonlinear programs. In particular, he studies the fundamental AC optimal power flow problem and its application in operations planning and pricing. He's also interested in the role of symmetry in optimization, particularly in integer programming, both in understanding its principles and in designing symmetry-aware algorithms. So, Matías, you can start now.
Thank you so much, Margarita. Let me put the timer. Thank you to the organizers. Today I'll be presenting some joint work with my co-advisor at Columbia, Yuri Faenza, and my collaborators, Victor Verdú and José Ferchay, both of them at Pontificia Universidad Católica de Chile. I'm a last year PhD student. At least 36% of the problems in MIPLIB 2010 have non-trivial symmetries. It is folklore knowledge that symmetry harms state-of-the-art techniques for solving integer programs. There's a substantial body of work on how to effectively branch on highly symmetric instances. But in this work, we follow a different direction. Here, you can frame the question as follows. So imagine that you are at the branch, you're at a particular node of your branch and bound tree, and you solve the LP relaxation, and then you want to understand whether you can cut off the optimal LP phase, which is symmetrical. It's very symmetrical, and so one of our goals is to understand whether symmetries affect the improvement of LP bounds, whether we are able to cut off the optimal LP phase under a particular set of cut operators that are called lift and project that I'll define shortly. And we would also like to identify group theoretic invariants that help us characterize the improvement of these LP bounds. And in a way, we'd like to abstract from particular classes of polytopes. So let me first tell you what do we mean by symmetric integer programs. So here on the left, you have a formulation for an integer program on 3 variables. So here, these are the integrality constraints. And on the right here, we see the optimal LP phase for this IP. Now, suppose that someone tells you that this solution is feasible for the LP relaxation. And now you can ask yourself, well, is this solution also feasible? Notice that here we permuted the second entry with the first. So let's look at the constraints. So if we swap the first and the second columns over here, we get the second row, and that's clearly satisfied about our initial solution. And if we do the same here, and we look at the second row and we swap constraints 1 and 2, we get the first row, and that of course satisfies as well for the initial solution. Notice that the third and the fourth row are invariant under permutations of the first and second column. So yes, we can conclude that the solution is feasible as well. And for this particular example, any permutation of a feasible solution is also feasible. So in general, we say that symmetries will be a group of permutations that preserve feasibility for feasible points of P. So now let me introduce a concept that is key for this work, and it helps us parameterize symmetry for polytopes. So we borrowed this concept from computational group theory. At least we are not aware of that this concept has been introduced in our community before. So let me tell you, let me illustrate this with an example. So we're going to say that you take a vector, a point in P, and we're going to say that P is one transitive if you can take any coordinate and you can map it to some other entry, right? So for instance here, and then still be feasible. So for instance here, your feasible point is X, right? So here we're mapping X1, we're mapping it to the third entry. and we're getting a feasible point. So if this holds true for any I1 index I1, then you say that the polytope is one transitive. So here, as I said, this is an example of just sending 1 to 3. Now you can extend this to tuples. So instead of just mapping one coordinate, you can map 2 coordinates. And the idea is that basically you are 2 transitive if you can map those 2 coordinates to other 2 coordinates and still be feasible. So in this case, we're mapping 2 to 3 here, and 5, the 5th entry, we're mapping to the 1st entry. And if this is feasible, and then for every tuple, then we say that the polytope is 2 transitive. So in general, you can generalize this to tuples of length k. Now, let me give you an example. So notice here that this is one transitive because like you can map any coordinate, any entry here. You have 3 different entries. And in these 3 vectors, we see that the entries, each entry appears once in each coordinate. So this is one transitive, but notice that this is not 2 transitive. Why so? Because if you swap these 2 coordinates, then the vector 1/2, 1, and 0 is not part of your feasible region. So then this polytope over here is only one transitive. On the other hand, this polytope, which is the convex hull of all the permutations of this vector, is 3 transitive, right? So we're taking all of the permutations of it. So you can say that this polytope has even higher degree of symmetry. Now, let me tell you what left-hand project operators are. And by doing so, actually, I'm going to tell you that by telling you what they do, right? So imagine that this is the convex hull of feasible integer solutions for your integer program. Now let's take P as the linear programming relaxation for that. And so what an operator T does, a left-hand project operator T does, is it takes as an input the linear programming relaxation. It gives you this convex set over here, TP. And then a key property is that when you project back onto the original space, you get a relaxation for your integer program that is at least as good as your starting relaxation, in this case, P. And so actually those are the conditions. This is the first condition that we have over here for the definition. And then what is key, of course, is that given that this is used for solving integer programs, you want to preserve feasibility of integer points, right? So here, notice that we are not chopping off any feasible integer solutions, right? And the third condition is a condition on monotonicity on the sets that you apply this operator. So this is a very broad definition, and in fact, there's many operators that are out there in the literature which satisfy these constraints. And here I'm depicting a partially ordered set of by strength of the operators. So let me tell you what this is. So this is usually known as the lift and project closure. Then this is asz-Schrijver. This over here is Sherali-Adams, which is stronger than this too. But Sherali-Adams is not comparable to asz-Schrijver with a p.s.d constraint. And on top of them is Lasserre, okay? So these relaxations the relaxations that these operators can produce can be very different. We're gonna say that Tk denotes the operator applied k times. And in theory, these operators Tk can be computed in polynomial time, but that's for k constant or fixed. But in practice already, for some of them, computing 2 rounds is already challenging. So now let me tell you about our first theorem. So this, a way of interpreting this is as follows. So as I said before, let's go back to our optimal LP mindset. So you're at the root node of your branch-bound tree, and then you solve the LP relaxation, and then imagine that there's no integer points on that optimal LP phase, right? And that's highly transitive, right? So in this case, it's k+1 transitive. So this theorem is telling you, it's giving you a condition, that's the first statement, whether you'll be able to certify that optimal LP phase is integer empty or not. So if this condition holds, right, then all of these operators are not able to certify that this optimal LP phase has no integer points. So in a way, you can think of this as a kind of like a characterization of a cutting plane proof for these operators. And moreover, this theorem is telling you that there's a hierarchy collapse for these operators. So as I said, I showed before, there's a partially ordered set, but actually when you're thinking, when your instance is highly symmetric, in this case, K plus one transitive, then K transitive, then all of these operators have the same strength. Either if one of them cuts off if the strongest one cuts off the optimal P phase, then the weakest one as well cuts off the optimal P phase. So let me illustrate this theorem with an example. So let's go back again to our optimal P phase that I showed at the beginning. So so first you can see from the picture that this polytope has no integer points. We said before that this polytope is 3 transitive. So let's apply our theorem with k equals to 1, right? So then n is 3, k is 1. So then this condition 1 is telling you, statement 1 is telling you that P intersects all of the 2-dimensional faces of the cube. So actually, you know, if you look at the picture, clearly you're touching all of the facets of the cube. So then that means that one round of any of these operators is not going to be able to certify that this polytope is integer empty. And actually here, if you see at the right, this gray area is this gray polytope over there is the lift and project closure applied to this to the optimal P phase. Now the pink area, the pink polytope is Sherali-Adams level 1, right? So notice that this theorem as well is not telling you that the relaxations are the same. It's just saying that the theorem is saying something about the strength of the operator in certifying integer emptiness. But here we have a small example where we see that the relaxations are not necessarily the same. Now let's apply this theorem with k equals to 2, right? So then this would be 3 minus 2 is 1, right? So then statement 1 is whether P intersects all of the one-dimensional faces of the cube. Well, clearly it's not the case, because if you see this edge over here that's one-dimensional is not being touched by P. So then that means that even the weakest operator here, the lift and project closure applied 2 times, is going to be able to certify that this polytope has no integer points. So you're able to chop off the optimal P phase for this instance. Now let me present to you guys a second theorem. So this was stated at the workshop, at the poster, as a working conjecture, and we're very happy that we were able to prove this for during the summer. And actually here we dropped the condition on the dimensionality of P. So now it's the theorem that we had before, but now we don't have the condition that P is not full dimensional. Okay. Now the catch is that we still don't have the so notice that before we were saying that we also have this for LS plus. Given that the proof technique is different, we still haven't proved that for LS plus, but we do have the hierarchy collapse for this 3 operators in the case with arbitrary dimensions. So now let me tell you, let me show you how you can use this theorem with a very cool example. So, and we can see the power of this theorem. So this PCC denotes the cropped cube. Okay. So imagine that you have a cube and that you chop off all of the vertices of the cube, right? So you get this cute picture over there. You chopped off the vertices. Well, given that you're chopping all of the vertices, clearly this polytope is integer empty, and at the same time you can show that it's n-transitive. Okay. So it's highly symmetric. Now, in 2001, Goemans and Toncel, they showed that applying n-1 rounds of Lovász-Schrijver is not enough to show that this polytope is integer empty. Okay. And at the same time, Monique Laurent in 2001, she also was able to show that even applying Sherali-Adams n-1 rounds, or Sherali-Adams level n-1 is not able to certify integer emptiness. But with our theorem, we can get this like immediately by looking at the following condition, the condition 1, that the condition on the intersection of the faces. So let's do it. So now we want to show this for k equals n-1. So then condition 1 is telling you that P intersects all of the one-dimensional faces of the cube, right? And as I said before, the crop cube, the only faces of the cube that's not touching are the zero-dimensional faces of the cube. Well, and you can also see in the picture that you're touching all of the edges. So this is giving you for free that applying n-1 rounds of Sherali-Adams is not able to certify that this polytope is integer empty. So that's it. So like, let me wrap up. So for key takeaways, the more symmetric the optimal LP phase, in general, the hard to cut, at least under these operators. So, you know, for people working on solvers and such, well, I guess that they already know that these cuts are kind of expensive, but still try to stay away of these cuts if you have a highly symmetric instance. And something else that we have is that there's a hierarchy collapse for this operators under symmetry, which we think is very cool. And for future work, we're working on partial symmetries, for instance, trying to extend this idea of like not of a group action acting on a subset of the variables and not all of the variables. We're also interested in looking at other hierarchies, for instance, Lasserre, and even other integer programming closures and different type of cuts. So that would be all. And if you folks want to explore more of my work, please visit my webpage. That's right over there. So that would be all. Thank you so much.
Thank you so much, Matías. So we will